taken a cube out of the earth. This upper surface is our map surface. We would envision this as being to the north, so this is a north-south cross-section view here. This would be an east-west cross-section view here. And what we had were a series of orientations of folds where we were looking at strike and dip of the hinge surface. And then we were looking at trend plunge of the hinge line. And after that, what we would think about is what is the pitch of the hinge line in the hinge surface. So how did we do? Okay, great, perfect, not quite so perfect. Which one caused troubles? Tim?
I felt like it might not necessarily have been any in particular that caused issues, but more general questions that
Okay.
I know our group wanted to rectify. We were curious about making sure that we understood what the difference is between, even though we have a verbal definition of pitch, if it's the angle of a line within a plane, we want to make sure we understood the difference between pitch and, say, some of the other definitions that are you've written up on the board.
Okay, so if you will allow, let's go back to this silly podium, which I don't know why they put podiums in classes. By definition, if we have a plane, and this plane is inclined, our strike line here is defined as a horizontal line in the plane. And so we define the strike line as that horizontal line in the plane. Then we look at its orientation relative to magnetic north. And so if we took, for example, something around in here, we would start off at north, and it looks like we would go about 45 degrees toward the west to define the orientation of that line. That would be the strike line. The dip, if we look on edge, the dip is this angle that is measured perpendicular to the strike, and it's this vertical angle from the horizontal down to the plane. And so the way that we denote that is we would have this sort of symbol, and we would write the dip angle here. And this dip looks like it's about 17 degrees. Okay? So this, in this case, we would have said north 45 degrees to the east, 17 towards to the west, 17 to the southwest degrees. We could have denoted that as simply 0, 4, 5, but in this case we would have to modify that to 315 to then have 17 southwest. Okay? So if we then have a line, let's put a line in our plane here. This is some type of lineation. That might be the trend of a fold hinge, that might be some sort of lineation within a feature. We talk about the orientation of this line. We talk about the direction in which the line is going down. That's our trend. And so right now my trend is right towards Sam. So that we have here an orientation that looks like it's going to be about 210. We talk about the plunge, which is this vertical angle here, which would be probably 12 degrees in this case. Then we talk about the pitch of that, and the pitch is simply the angle within the plane itself measured from the strike line, measured from the horizontal line to the plunging line. That's the pitch. Okay? So we use those different descriptions of orientation to talk about strike and dip, trend and plunge, and then pitch. Because if you recall, when we had our folds, we would have, in this case, upright horizontal. Our hinge line was horizontal, our hinge surface is vertical. Plunging, hinge surface is still vertical, or the hinge line is now plunging. A vertical fold, both are vertical. But if we do a recline, now I'm going to rotate around the horizontal line here. Now I have my hinge surface dipping, my hinge line is plunging, but my pitch is 90. If I come back up, this is inclined, dipping, hinge surface, horizontal hinge line. This is recumbent, horizontal hinge line, horizontal hinge surface. If I come back here and do this, I have a dipping hinge surface and a plunging hinge line, but my pitch is less than 90 in this case. So that we have these different orientations that help us describe the orientations and interpret the orientations of folds. Because when we look in the field, we have folds. We know that folds occur on all scales. We know that they occur on all materials, and they can have a wide range of orientations in that system. And those will reflect differently depending on what the orientation of the fold is relative to the local topographic surface. And that 3D visualization is part of the reason that we have these simple block diagrams, which turn out to be not quite so simple. The block diagrams can be a little bit challenging to visualize because you're trying to visualize and understand what those folds are actually doing, based sometimes on limited observations, based sometimes purely on what you can see at the map surface, and then we are interpreting what's happening down here. So if you're good with those, let's go ahead and turn those in. And we'll try to get those back to you. Thank you, Mina. We'll try to get those back to you this week. Thank you. Thank you. Yeah, do we have? You do? Okay. Now, what we want to do today, we want to think about how do folds form, a little bit more information on folds and fold systems. And then we're going to just briefly touch on rock fabrics, development of rock fabrics, and a little bit of metamorphic geology as it pertains to structure before we jump into the next topic, which will begin looking at some vector-intensive calculus, a little bit of work on stress systems, stress fields, how do we describe those, as we start to move towards the more mechanical description of how materials actually behave.
Chapter 4 of the book relates to stress, but how about the metamorphic materials you were just discussing? Do you know what chapter that might pertain to?
Tim, I don't. I think it's in foliations and fabrics, lineations. I will check. Okay? Now, what we have learned about folds is we find them in all rock types. We find them in all conditions. And by all conditions, I mean all different fault systems, all different sorts of loading conditions, folds seem to form. So they really are a fundamental response of rock materials, particularly layered materials, to deformation. And they preserve a beautiful history of deformation, strain. When we think about folds, we've been fairly simple about our descriptions of folds. We know they form at all scales. We have folds that are just hand sample size, like this one. Lovely little fold you can carry around in your pocket. We have folds that are 20, 30 kilometers across in scale. So folds can be huge. They can be microscopic. There are some interesting relationships with thickness in a system. What we know about folds, we want to keep relatively simple, but the general concept of folding is that it is likely a type of buckling response. And we can visualize in the most simplistic sense that we are buckling either a beam or some type of a plate, a shell in that system. And so if we put the most simple thought up here, I have drawn a simple beam. We have some sort of a confining medium above and below our beam, and what we're going to do is we're going to shorten. What's going to happen? Well, we can predict this. This is easy. If we take something as simple as these cards, if we take this and start to compress, what's going to happen? It bends. Every single time we sit here and go for hours and hours and hours, it's going to bend every single time. And so buckling is a fundamental response of a material to loading. The interesting things to note is that as we begin to buckle, the initial phases that we see in the buckling process, particularly if we have a perfect beam, no irregularities in the beam. If it's a perfectly flat, smooth beam, it will shorten about 10%, so that the phases %, shortening, and then we will buckle. The buckling will appear almost instantaneous. So it will buckle, begin to buckle quickly, and then as we continue to shorten, what happens to our amplitude? Any guesses?
It increases.
Yeah, it's going to increase in the system. So our amplitude continues to grow. In the case of a perfect beam, then we see what is called a dominant wavelength. We see a single wavelength that will develop out of our system, so that we will have this nice perfect fold that will develop. And the wavelength of that is termed LD, dominant wavelength in the system. That is going to depend on several factors. Thickness. And that makes sense. If it's a really thin fold, the dominant wavelength will be relatively short. If it's a really thick layer, well, the dominant wavelength will be relatively long. It will depend on the strength of our rock and our ratio here of strengths. So we're saying that this is strong, this is weak. The greater the difference between the two, the greater the wavelength that we will see in our system. So thickness, strength of that system will control what that dominant wavelength will do. A degree. If we look at thickness, if we have a really thick layer, then we will have a very long dominant wavelength. If we have a really thin layer, we will have a very short wavelength. And that is intuitive. Imagine if we have, this is a thin system here, thin layers. What if I had something where I had a stack of cards that was 1 meter high and I'm trying to shorten it? It's going to be a lot more difficult, and I would form a much, much longer wavelength within that system. And so this dominant wavelength responds to the types of materials, the thickness of the layers. But we have a problem with our model, because we know that we find folds on all scales. If life were this simple, we would only find a few scales of folds. We would not find folds necessarily in metamorphic rocks. We would not necessarily find folds in igneous materials as well. And so we've got an issue. And if you recall, we have mentioned the concept of parasitic folds and fold vergence. And so let's go back and think about this. So let's draw a line here. This is going to be our ideal imaginary world. And so this would be the Peter Pan side of things over here. Second star to the right on to morning. But in the real world, what we see is that very often we will find folds that look like this, so that we have, I'm going to draw a general fold outline here, and we find smaller scale folds superimposed onto the larger scale folds. Now, I'm not going to put a scale on here. This might be 30 kilometers. It could just as easily be a half a meter or even smaller. And we find these smaller scale folds that are superimposed, so our fold geometries are not simple. Now, if I were to fill this out appropriately, then what our layers would look like would be this. So our fold would take on a rather intriguing shape, and we would see these smaller scale folds superimposed. So now let's go back and let's look here in our imaginary world. How well does our theory fit? Which one of these is our dominant? Let's say that we're in this case, let's say that we're working in the Appalachian system, and what we're seeing is that we have an anticline-syncline pair that is 45 kilometers across. And then we find folds, anticline, syncline couplets within that anticline, syncline, large anticline, syncline pair, that's called the Mazanutten synclinorium, that are 5 kilometers across. Then we find folds that are 1 kilometer across. Then we find folds that are 100 meters across. Then we find folds that are 1 meter across. And then we find folds, then it gets kind of frustrating by this point, we find folds that are 10 centimeters across. So that we find folds on folds on folds on folds on folds. Well, which one of those is the dominant wavelength? We have a problem. And the problem is trying to describe how does this folding process start. And so what we have to do now is imagine, again, we're going to come over here to the imaginary world. Rather than having a perfect beam, let's keep it relatively simple. And I'm going to have a beam that looks like this. Okay, that's a single beam, but this is strong, this is weak. What's going to happen in this particular case? Well, now we have a greater range of wavelengths that are available to be amplified. And so we may start seeing something akin to this develop. And the trick is to try to understand what wavelengths are present initially. And when we think about that, we start asking some bizarre questions. We start saying, well, gosh, in a carbonate platform, what wavelengths would be available depositionally to now be folded in a deformation event? Would a carbonate platform present a different set of wavelengths than would a fluvial deltaic system? So that if we go back in class, all the way back to the beginning of class, we were talking about primary depositional features. Now those primary depositional features, they were originally intended to give us Younging direction. Tell us which way's up. And it's always good to know when you're walking down the hallway which way's up. Now we're going to actually have to rely on those to help us determine what wave numbers, what wavelengths are available to be amplified in the folding process, and do they sort out to be these parasitic folds? That is a question that I must confess we don't have an answer for right now. That's an area of active research, because one of the big questions, and in your notes I think I interjected a very quick description of Fourier analysis. Basically, if you have a continuous function, and we can think of this as continuous, we can describe it as a rather interesting infinite series sine-cosine couplets, where the sine and cosine couplets are integral types of systems. So that we have now the ability to start describing what is this domain going to look like.
You said what the primary deformation features we use for what?
Primary depositional features
Deposition.
that we used for Younging direction.
Mm-hmm.
So now we have to think about what is the Fourier domain here? Mathematically, can I describe this as a bunch of sine-cosine series? Then if I can come up with, and there's a big if right there, if I can come up with that, can I come over here and squish it and determine which ones will amplify, when they will amplify, and will they contribute to this type of deformation for a single layer beam, for a multi-layer beam in that system. And so it's still an area of ongoing research. There are significant numbers of questions. We've not yet successfully come up with a good Fourier description of even a carbonate bank to then take it into a folding model to try to understand what's happening in the system. So, the things to take away from folds, all scales, all materials, under all conditions, they give us a fascinating history of how systems behave. Folds in and of themselves are beautiful things. Folds are probably my favorite thing in structural geology. They are just gorgeous. But we know if this board were the sum total of knowledge, then what we know about folds is that much. See that, Mark? Right there, yeah. That's about how much we know today. And so there's still a tremendous amount of work to be done. Those people who work on folds, we basically feel like idiots most of the time because we know so very, very little about how these systems behave. Okay, questions about folds? Because Tim.
Sorry, how, it's Fourier transforms.
Fourier series, Fourier transforms. You use Fourier transforms, for example, if you have this as a wavelength domain, you can transform it into a wave number domain so that you can play with, you can transform back and forth and find solutions in whichever one is easier to solve. And if you need someone that is a specialist in that, then look to the back of the room. In that seat right there. Yeah, right there. Jabo is absolute specialist in Fourier transforms, fast Fourier transforms, and those sorts of systems. So there's a tremendous amount of work that needs to be done. So, we're good?
What were you trying to illustrate with that diagram? Were you just saying which is the major fold versus?
Well, the real question, one of the real questions, and when we find these parasitic folds, you can see that we have the Z vergence, the S vergence, the M vergence in the system. What's the dominant wavelength? You know, is this a dominant wavelength for this layer? Is this a dominant wavelength for that layer? How do we separate that out? And from our perfect beam, we realize we can't get there from here. We can put this into a finite element model. We can deform it all day long and never get to that.
But you can't you pick like minimums and then maximums and then like you compare them. Well, wouldn't you just like break that off and not take it as a whole and then just take it?
You
as
could,
a single
yes,
piece?
you could discretize the system and then try to link it
And
back.
then create the dominant one
Of each, and then some back and forth across.
Yeah.
But then we have linkage issues. And when we try to transform back, things get a little bit dicey.
Isn't that all materials then?
Yes. So it becomes an intriguing challenge in there, because if we did, as an example, let's say that we were to
So just
do.
think about how like when people like design buildings, like the beams.
Yes.
The exact.
Because we know the couple. If we look at, let's take a multi-layer beam here that has that geometry. Now, we really don't know how much slippage we're going to be able to have. We don't know whether we have lateral changes in strength in the material. We have to worry about, in this case, let's say we start to buckle, this starts to grow up, this starts to grow down when do they begin to interfere in that system? And so the linkages between the layers have not been worked out well. And so we can't isolate them out necessarily and take them back to the original. We can take them back to an idealized original, but not back to the absolute original. And it may not, meaning it may not be possible to fully go from there to there or back. Or let's say, we haven't been able to do it so far. And there have been some extraordinarily bright people working on it that so far we haven't gotten there. Okay, does that make sense? Now, the next step, the next thing we want to talk about is very, very often when we find folds, let's say we have folds that look like this, what we see is that we will have some type of a rock fabric develop associated with that fold. And a lot of times that rock fabric will tend to fan. In this particular case, we are going to term this a rock cleavage. And the way that we define a rock cleavage is that we are going to form a new surface in a material where it's a new surface, but it is not due to fracture. It forms either by flattening and changing the shape of grains or growing new materials in the rock itself. So we can form it due to flattening of grains or growth of material. And then there's one specific case that is called pressure solution, where we actually dissolve material to form now a new surface in the material. And I brought some examples as a lead-in to metamorphism. I have two samples here. This one's a little bit dark, a little bit more difficult to see. If we look at this one, this is out of the hinge of a small fold, one of those small parasitic folds. This was a fourth order parasitic fold, so it's a fold inside a fold, inside a fold, inside a fold in this system, right in the hinge zone. And what you should notice is that you've got some orangish brown lines that are vertical here. Those are pressure solution surfaces. You'll also notice that this central part is folded, where we don't have the pressure solution surfaces. This was flattened this way by quite a bit, squished. Here you see these beautiful little buccal folds. They're about 1 centimeter across. You see the pressure solution surfaces here and here. Let's send that around that way. This one, a little bit harder to see. If you look at the back side, Tim.
Why don't you see the pressure solution lines along the folds?
Because they're a different material that wasn't quite soluble under those conditions. If you look at the back side, you see some lineations here. This is a type of cleavage. If you look The best way to look at it is let the light shine off and you'll see a zone that has these short lines spaced out, zones that don't, and again, zones that do here. Those are pressure solution surfaces. So this is a type of pressure solution cleavage under low-grade metamorphic conditions. Okay? Two different examples. If we look at this particular sample, this one is close to being a slate. It's not quite a slate. It would have rung if it were a true slate. This is a volcaniclastic out of the Appalachian system. This is up high in the Blue Ridge, along the Blue Ridge Trail, along the Appalachian Trail. This is a Cambrian-aged volcaniclastic system. If you look on this side here, you'll notice that layering is oriented about like so. This is layering, but you have a very strong fabric here that is vertical. This is an incipient slaty cleavage in this particular case. And so this system, you have an incipient slaty cleavage. This one is a folded, this is a crenulated, again, not quite perfect slate, but a crenulation slaty cleavage at a slightly higher pressure temperature than the first two samples. And so what we want to start thinking about is what role does metamorphism play in the formation of fabrics and in the formation of new materials. Now, if you recall from physical geology, remember you talked about slates forming then schists, then gneissic systems as being the higher grade metamorphic. And the question is, do you recognize those? If we were to look at this, what would you call this? It's got nice, shiny, big muscovites in here. It has a fabric cutting through here. When I look at it, I see a great deal of garnet, a few starlights, mostly garnet.
Higher grade.
Is this a slate? Is this a schist? Is this a gneiss? Well, take a look. And we have a slightly different one here that has beautiful garnets in it. It's actually got a few starlights in it. Two different kinds of mica. There's a disorganized 2M mica, and then there's a nice muscovite in here. Starlight, garnet. Now, is this a, what is this? Is this a schist? Who wants it to be a schist?
I want it to be schist.
You're right.
Yeah.
It's a gold star for Ireland. That is a schist. If we go up into higher grade, here we have a rock. This is off of Highway 14A in between Douglas and Lovell, Wyoming. What you see are these beautiful feldspar algans floating in here. These are porphyroblastic in nature. They get strained out. They're actually porphyroclasts that get strained out in the system. Is this a slate, a schist, or a gneiss?
Which sand was that?
The contents of this rock are feldspar, quartz, biotite.
It's lower grade.
Yeah, it looks nice, and so it's a gneiss. So what we find happening is that we see different textures with increased temperature. Initially, we will see slates form. We may see pressure solution at that same time. Then what happens? We begin to react. We begin to metamorphose to the point that we're replacing minerals. Key things to remember when we look at metamorphic systems. Is we want to think, and you typically see a diagram like this. You have protolith, you subject it to pressure, temperature over time, and then you have metamorphic rock. Well, this sort of representation can cause some misconceptions because the system in metamorphism is closed. We start off with some volume of material here. We have some initial chemistry. We then subject that to pressure, temperature, time, and we don't change the bulk chemistry. We change the minerals that form in that system. So we find new minerals that are stable, but we don't have flux across the boundary. We treat it as a nice closed system. So if we start off with quartz, clay, maybe a little bit of hematite, maybe a few other things, we're not going to form any minerals that do not contain those elements. You have an elemental balance across. And so that can lead to some strange things. If we look at this rock, this is part of the Baraboo quartzite, Baraboo syncline area. This is an extremely high-grade metamorphic rock. It looks like a sandstone because it started off as a quartz arenite and it's a quartzite. We didn't add anything, we just heated it. Same thing here. Here's a dolomitic marble. It started off as a dolomitic limestone. It's been metamorphosed to very high grade, and it's a marble, a dolomitic marble. So if you have calcium carbonate only to begin with, you're going to end up with calcium carbonate, metamorphosed. If you have quartz to begin with, you're going to end up just with quartz in that particular system. So we want to keep in mind that the system will remain closed. The minerals that we see, if you go back and you think of Bowen's reaction series, if we start with what is called how did Dr. Cornell term it? I call it a semite rock. Maybe you call it a argillaceous sandstone shale. First thing that forms is chlorite. Then you start picking up some biotite and garnet, then you pick up some staurolite, kyanite, and finally sillimanite. That's a closed reaction. Each one of those are just hitting their stability field relative to the pressures and temperatures that it is seeing. So we have these different textures. They can form different lineations. We can form some wonderful shear zone materials. This particular sample, this was sent to me by Andrew Matson. I think I told you Andrew's story. He did his undergrad here, went to Caltech for his doctorate. He's now at Oxford. This is the myelinite that forms within an extensional system. This is part of that. If we go back and look at our normal fault system, so that we have this large scale crustal block from the surface to mid-crust. That myelinite was right there, so there's Andrew picking up this particular myelinite. This is what we're going to term an ultra myelinite because of the fabric that we have in here. So we can see fabrics associated with folding. It's very common to see either a pressure solution or a flattening cleavage associated with folding. As we continue to deform, we can develop a wide range of metamorphic textures and a wide range of structures in that particular system. And so these are examples of some different types of metamorphic rocks. This is out of a shear zone. This is this is out of Goodyear's Fault along Highway 49A in California, Yuba River. Fantastic drive. Absolutely great trout fishing too. So this is a green schist out of that system. Do you remember your different metamorphic grades? So if we got a couple of minutes, we can draw that up. You remember your different metamorphic grades, fabrics, rock types. If we look at temperature here increasing, pressure here increasing, we saw a zone of hornfels. This would be green schist, blue schist, then as we approach our melts, this would be granulite and eclogite. So that with increasing temperature, green schist, increasing pressure, blue schist. Down here we end up with zeolites. This is our zeolite, pompelliite, freenite zone for the lowest grade conditions in that system. So all of this deformation that we've seen can occur in each of those rocks. You can see some green schist in southwestern or southeastern Oklahoma. Blue schists, the closest blue schist that I'm aware of are in Colorado. Hornfels, we can see some great hornfels in Colorado. Granulite, if you go to Santa Fe, New Mexico, drive from Santa Fe to Taos, you can find some beautiful granulites, eclogites, Blue Ridge. All right, so next time we will start stress.
What would be the small t in that system?
Time. Pressure, temperature, time. These reactions always take time.
Okay.
Okay. Questions? All right, then see you guys on Wednesday. I would not be surprised if we had a block diagram on Wednesday. That would not surprise me at all.